In our last video, we discussed one of the simplest filters used in electronics, a passive first-order RC filter. This filter can attenuate high-frequency AC signals while it passes through low-frequency AC signals. As we have already seen, this little circuit does the trick in principle, but its behavior is far from ideal. A major problem is the unsatisfying decrease of attenuation for signal frequencies above the corner frequency. Fortunately, there are quite a number of solutions for this problem, which all have their strengths and weaknesses. So let's take a look at some of the more elegant filter circuits and their application. In this video, we again want to focus on passive filters only. We already know the simplest type of those circuits, consisting of a single capacitor and a resistor. The capacitor is often used for passive filter circuits because it is easy to manufacture, costs little money and behaves quite predictable. So let's stick with it for the moment. To increase the slope of attenuation of this circuit, we can simply daisy chain a few first-order RC filters. Every additional capacitor increases the so-called order of the filter. 3 RC low passes in a row will hence give us a third-order low-pass filter. Every stage of the filter will increase the slope of attenuation above the corner frequency by -20 dB per decade. You can see this in the transfer function. A first-order filter will decrease the output voltage by -20 dB compared to the input voltage. A second-order filter will attenuate the signal by -40 dB per decade. A third-order filter will lead to -60 dB attenuation per decade, and so on. This can only work if we keep the input and output impedance of each individual stage in mind. Every additional stage will always influence the behavior of the previous one. A good rule of thumb is to ensure that the input impedance of every stage is at least 10 times larger than the output impedance of the previous one. But how can we calculate these impedances? It's easy if we think of the worst case for both, that is minimum input impedance and maximum output impedance. In order to do this, we look at the two extremes regarding the input signal frequency. In both cases, the influence of the capacitor vanishes, either because it behaves like a short or like an open circuit. The answer to the question, what's the worst case input and output impedance, is therefore astonishingly simple. It's R for both cases. So according to our rule of thumb, all we have to do to ensure the independence of each stage from the previous one is to make the value of R at least 10 times higher for each stage we add. But not so fast. What about the corner frequencies of each individual stage? As we have seen in our last video, the corner frequency is defined where the value of the resistor R is equal to the length of the impedance vector of the capacitor ZC. If we want to increase the resistance to 10 times its original value, we must also increase the length of the vector ZC at this exact frequency by 10 times its value. Since the frequency is fixed, we can only change the value of the capacitor. Consequently, for a 10 times higher value of R, we need 1/10 of the value of C to ensure that the corner frequency stays the same. Actually, the definition of the corner frequency comes from the input and output power of the circuit. Since the amplitude of the output voltage at this point is 1 over the square root of 2 times the input voltage, the output power, which is proportional to the square of the output voltage, is exactly half of the input power. Makes sense, doesn't it? Adding RC stages to get higher order filters is one way to improve the filter characteristic. Unfortunately, this technique has two major drawbacks. On the one hand, the resistor gets 10 times bigger with every additional stage we add. until at some point we simply cannot drive the load anymore. On the other hand, the capacitor will become very small at the same time until it reaches values of some picofarads where we practically cannot reduce the capacitance any further. So if we want to build higher order passive filters, we have to find other ways. Fortunately, there is another important yet little more bulky passive component which can help us to solve this problem: the inductor. Just like with the capacitor in our last video, we can connect a resistor and an inductor in series, which will give us a simple high-pass filter. For low frequencies, the inductor will behave just like the wire it is, and will short the output to ground. With higher frequencies, the inductor will gain impedance and the output voltage will rise. For very high frequencies, the inductor will behave like an open circuit. Since no current can flow, the output voltage will be equal to the input voltage. As opposed to the impedance of a capacitor, which decreases for high frequency signals, the inductor's impedance will rise linearly with higher frequencies. Its impedance ZL is equal to J omega L, where, similar to the capacitor, the J stands for the imaginary unit, omega for the angular frequency, and L for the inductance. We can now combine the effects of inductor and capacitor to build higher order low-pass filters. If we want to describe the behavior of this second order low-pass filter mathematically, we can do this by dividing the output voltage by the input voltage, which is equal to dividing the output impedance by the input impedance. If we multiply this term on the right side by J omega C, we get this expression. Since J is the square root of -1, J squared will simply give us -1. Finally, we are left with this equation, which is very interesting for two reasons. First, we can see that this term gets rapidly smaller for higher frequencies, since omega in the denominator is squared. Secondly, we notice that this expression can approach infinity if omega squared times LC becomes 1. This will happen at one particular frequency. We can calculate the so-called resonance frequency. To do so, we set omega squared times LC to 1, and we get a frequency of 1 over 2 times pi times the square root of LC. But what happens here? Didn't we want our filter to dampen high frequency signals, not amplify them, much less reach values close to infinity? Of course, our theoretical approach is, like always, only a contingent truth in the real world. Real-world inductors have an intrinsic resistance, which we must add to our circuit to get to the bottom of this. With an additional resistor, our circuit becomes a little more realistic and our calculated behavior a little more complex. At least now it's clear that the amplification at the resonance frequency is always limited by our resistor. If we vary the value of R, we also see that we can influence the behavior of our filter. A change in R not only affects the amplification at the resonance frequency, but consequently changes the attenuation, which leads to different 3 dB corner frequencies for different values of R. We can also vary the values of L and C interdependently, such that the corner frequency stays the same. All these degrees of freedom can be used to alter the so-called characteristic of the filter. There are some important designations for the most common filter characteristics. The ones you will probably see most frequently are called Bessel, Butterworth and Chebyshev characteristic. All of them have certain advantages and disadvantages. A Chebyshev design, for instance, has the steepest attenuation of all, which comes at the expense of flatness in the passband. It also has only mediocre phase and transient characteristics, which will produce unequal time delays for signals within the passband. As a result, the waveform of a signal in the passband will suffer distortion, which can be undesirable. So if we want a filter with constant time delay, also called a linear phase filter, we rather use a Bessel characteristic. Here the waveforms of all signals within the passband will stay exactly as they were. But then again, the Bessel filter cannot compete with the Chebyshev regarding attenuation above the corner frequency. You see, filter design is a challenging task. First of all, you always need to know what the purpose of your filter shall be. This will often lead to specific requirements. Usually, the first thing to think of is the corner frequency, followed by the steepness of attenuation. The latter will give you the order of the filter. Finally, you can choose the filter characteristic. If linearity is an issue, a Bessel or maybe Butterworth filter is needed. If steepness is the major argument, Chebyshev will save the day. One might also think about component tolerances or even temperature variation, which can have quite an effect on the real-world circuit. Usually, all those demands will leave you with an allowable range of filter attenuation, which is often depicted like this. The graph shows you parameters which behave like borders for attenuation and frequency. For a satisfying design, they must not be crossed by the recorded frequency response. With all those requirements in mind, the numerical calculation of such a filter is a very challenging, if not depressing task. A few years back, designers used big books and large tables to calculate the values of all the components. Fortunately, nowadays you don't have to calculate anything by yourself anymore. There is a big variety of cost-free software to help you design your filter. We have put some links in the video description, so check it out if you like. The passive low and high pass filters we have seen until now are most commonly used in audio applications like crossover networks for HiFi speakers. These filters separate the low and high frequency components of an audio signal coming from the amplifier to drive a subwoofer or a tweeter. A second important application for passive filters can be found in switched mode power supplies. How these circuits work will be topic of another video. For now you only need to know that they cause high frequency distortions which must be filtered. Therefore, a low-pass filter is needed at the output of such a circuit. Three kinds of low-pass filters are very common for this task: the L filter, the pi filter and the T filter. Which one is best for an application is decided by the output impedance of the power supply and the input impedance of the load. To ensure the best performance of the filter, we always want an impedance mismatch in order to minimize the power transfer for high frequency signals. So for a source with low impedance, the first element of the filter must have high impedance at high frequencies, like the inductor does. If our load has also low impedance, the last element of the filter must consequently also be an inductor. If we put the capacitor in between, we get a T filter. Let's do another example to make things more clear. Assume our source again has low impedance, but this time our load has high impedance. What will our filter look like? Easy! The best mismatch for high frequency distortions coming from the source will require a high impedance at the input of the filter. We therefore again place an inductor as a first element. Looking at the output of the filter, we want a mismatch for the load with high impedance. We therefore need a part that has a low impedance at high frequencies, like a capacitor. The resulting filter will be an L filter. If you have a little time, you can now think about applications where pi filters can be useful. Loudspeakers and switched mode power supplies are not the only real-world application of passive filters. Another more outdated but refreshingly simple application of passive filters is the AM receiver of a car radio. If we connect a capacitor and an inductor in parallel, we get the so-called bandpass filter. The frequency response shows us its behavior. In practice, losses in the inductor will again limit the sharpness of the peak around the resonance frequency. We can use the passband of such a filter to demodulate an amplitude-modulated signal. Amplitude modulation, or AM, is a yesteryear's way to transmit a radio signal. Even though it's outdated, you can still receive AM radio in most parts of the world, because its principle is so easy. The radio station transmits a carrier signal with a frequency somewhere between a few hundred and some thousand kilohertz. The carrier signal is modulated in amplitude with the waveform of the audio signal. To hear the audio signal, you simply have to connect your radio antenna to an LC filter, then rectify and amplify the resulting voltage and put it to a speaker. A variable capacitor C1 will allow you to tune your desired station. A subsequent diode passes through the positive half wave of the carrier signal. R1 provides a light load for the rectifier, and C2 finally acts as a low pass to pick off the positive envelope, which is the audio signal you want to hear. If you have seen our videos about amplifier circuits, you can now try to build such an AM receiver by yourself. All you need is a long wire for the antenna and some basic elements, like an adjustable capacitor, an inductor, a diode, some resistors, and either a transistor or operational amplifier. Speaking of operational amplifiers, there's another important type of analog filter circuits, the so-called active filters, which we haven't covered yet. This is a big topic which deserves a video on its own. For now, we only want to take a short glance on the world of active filters to find another way to improve our passive circuits. Remember our problem with cascading simple RC low-pass filter circuits? The major issue here was that every stage has an influence on the cutoff frequency of the previous one. In the first attempt to solve the problem, we helped ourselves by increasing the input impedance of every stage. But there is an even better way to deal with this problem. We can make use of the pleasant features of an operational amplifier. As we have learned in one of our last videos, an operational amplifier has a very big input impedance and a rather low output impedance. We can put this characteristic to good use by connecting a so-called voltage follower to every output of every stage. Now the input and output impedances of every stage are completely independent, and the individual stages can therefore not influence each other. But beware of the pitfalls of operational amplifiers, because they have a frequency behavior of their own. But that's another topic we discuss in one of our other videos. There are even smarter ways to build active filters, which have the ability to amplify some frequencies of a signal while attenuating the others. We will work this out in detail in one of our next videos. If you cannot wait and want to know more about active filters, we have put some links in the video description. For those of you who'd like to do the arts and crafts, there is an additional link that describes how to build a do-it-yourself AM receiver, including some amplifier stages for headphones and 8 ohm speakers. Have fun building it and feel free to share your experience in the comment section. I'm Michael with the Institute of Electronics. We hope you've learned something today, but anyway, thanks for watching. If you want to learn more about filter circuits, we highly recommend The Art of Electronics by Horowitz and Hill, as well as elektronische Schaltungstechnik by members of our institute.